Welcome back. In this segment, we're going to analyze the time complexity of the merge algorithm that we discussed in the previous segment. So here is the algorithm again. I'm not going to go through it. Make sure you review the previous video if you need to. This time, I want to perform the time complexity analysis of this algorithm. So the first question is, how are we going to measure the input size? Well, what is the input to this algorithm? It's the two sequences A sub I and B sub I. Now these sequences are finite, so let's call M the length of the first sequence, that is the number of terms in that sequence, and let's call N the length of the second sequence. So the runtime of this algorithm will be a function of these two numbers. Let's call that function f as usual. Now here we have a couple of choices. We could compute the runtime f as a function of two arguments, m and n. But another way, which is the one we're going to use in this analysis, is to simply take the sum of the two lengths, m plus n. Notice that makes sense because the length of the input is proportional, obviously, to the number of elements in both sequences. So in conclusion, we're going to take our input size to be measured as m plus n, where m is the number of terms in the first input sequence and n is the number of terms in the second input sequence. The next choice we have to make in our time complexity analysis is the type of primitive operations that we're going to count as measuring the runtime of the algorithm. Now remember that one characteristic of a primitive operation is that it takes constant time to execute. In other words, its execution time must not depend on the input size. So I want to argue here that every operation in this algorithm is a constant time operation. And to convince you of that, I'm going to ask you to keep in mind a particular implementation of finite sequences as a linked list. In fact, let's consider doubly linked list, where every integer in a sequence has a pointer to the next integer in the sequence if it has one, and also a pointer to the previous integer in the sequence if it has one. And this data structure is going to have a pointer to the first element in the sequence and a pointer to the last element in the sequence. Now, if a sequence is empty, then these two pointers will be null pointers or null references. So, keeping this data structure in mind, let's look at every operation in this algorithm and make sure they can be executed in constant time. So this first step here is easy. You can just build an empty sequence data structure and assign it to a variable. That's definitely constant time. Now to check that a sequence is empty, you just need to check the head pointer, the pointer to the first element, and see if it's a null pointer. That's also constant time. To look up or access the first element in a linked list, you just follow the head pointer. Again, that's constant time. Comparing two integers, of course, is a primitive operation. Inserting an integer into a linked list, especially at the end of the linked list, is constant time. We can use the pointer to the last element to do that. Doesn't matter how long the sequence is, the number of pointer operations is always the same. And similarly, deleting the first element from a sequence is also a fixed number of pointer operations. And then appending two sequences is constant time because all you have to do is to manipulate the pointers of the last element in the first sequence and the pointers of the first element in the second sequence to stitch them together. That's definitely constant time. So you can see that any operation in this algorithm can be implemented in constant time, and therefore we can pick any one of them as a primitive operation as long as it's representative of the total runtime of the algorithm. So for example, let's say we pick this operation as a primitive operation, this appending of two sequences. Sure, that operation takes constant time, but the question is how many times does it get executed when this algorithm runs? Well, it only gets executed twice if you count these two operations here, which are identical. Well, that's not representative of the runtime of the algorithm because this gets executed only twice, which is a constant time that does not depend on the input size here. So instead, we must pick a primitive operation that is executed a number of times that is representative of the total runtime. So of course here, the crucial part of the algorithm is the while loop. So we can ignore this primitive operation here, which gets executed only once, as well as those last three. We need to focus on the while loop. So one question is, how long does it take the while loop to execute? Well, we already argued that these are constant time operations, so are these, and notice the runtime of the then block is exactly the same as the runtime of the else block in terms of number of primitive operations. So this if then else block always takes the same amount of time, and that's constant time. Since these are constant time operations as well, we see that the execution of the whole body of the while loop takes constant time. So the bottom line here of this analysis is that the runtime of this algorithm is proportional to the number of times that this while loop gets executed. So now all we have to do is to pick a primitive operation that executes a number of times that's proportional to the number of iterations in the while loop. And it turns out a good choice of a primitive operation would be, say, this operation right here, the comparison in the Boolean expression of the if statement. So in conclusion, we're going to count the number of times that the while loop is executed, and more specifically say the number of integer comparisons. So the last step in the analysis is to count the number of iterations executed by this algorithm. So what does the while loop do again? Remember, at each iteration of the while loop, one element of the input sequences is taken out of its input sequence and added to the result sequence. So that's one iteration of the while loop. And therefore, for every iteration of the while loop, one of the sequences gets one term shorter. And the termination condition is when one of the sequences becomes empty. So one thing that should be obvious right away is that for a particular input size, m plus n, the number of iterations will vary depending on the length of the input sequences, even if the total stays the same, say m plus n. For example, if one of the sequences only has one element, so m is equal to 1, say, and the element in the first sequence or in that sequence is smaller than all of the elements in the other one, then the while loop is going to be executed only once. Namely, you will take that element out of its sequence, add it to result, and then that sequence is empty and you stop. On the other hand, if m and n are equal, then you're going to have to go through at least all of the elements of one of the sequences to empty it. And so the runtime in this case for the same value of m plus n is going to be larger. So the bottom line here is that there's not just one time complexity for a particular value of m plus n. We have different cases. We have base cases, worst cases, and of course we have the average case. So for this time complexity analysis, let's choose the worst case time complexity because that's the one that gives us useful information and that's the easiest to do. We're going to skip the average case time complexity because it's quite a bit harder. And we're going to skip the best case time complexity because the best case is not very informative. So all we have to do now is to compute the number of iterations that are executed by this algorithm in the worst case for a particular value of m plus n. So another way to look at the while loop is to realize that for each iteration of the while loop, the result sequence is increased by 1, since you insert one more element into it every time. Since the result sequence starts empty and ends with a total of m plus n elements, it should be obvious that in the extreme worst case, the number of times that this while loop is executed is at most m plus n times, because that's the total length of the result sequence at the end of the algorithm. And again, during every iteration, only one element, or exactly one element, gets added to the result sequence. So this argument already allows us to conclude that the runtime of this algorithm, f of m plus n, is big O of m plus n. In other words, an upper bound for the runtime of this algorithm is directly proportional to the value of m plus n. Now, while we just argued that in the worst case, the runtime of this algorithm is m plus n, you might think that this upper bound is too large. Because remember, at the end of the while loop, one of these sequences is not empty, and we're going to add all of its remaining elements to the result sequence in one step. So it's quite possible that this upper bound is much too large. So the next step will be to prove that f of m plus n is also big omega of m plus n. In other words, that this is a tight upper bound for the runtime of the algorithm. And to prove this, I'm going to show you how to build two input sequences that will guarantee that the algorithm will be, or its runtime will be, proportional to m plus n. So let's say we take two sequences, the first of which has 5 elements, so m is 5, and here I'm showing you the first 4 elements of it, 1, 2, 3, 4, and then the second sequence will have 4 elements, so n is equal to 4, and I'm showing you here the first 3 elements in that sequence. So notice I inserted the elements in order. Since they have to be sorted anyway, I might as well use consecutive integers. And the key for this example to work is to make sure that these elements taken together are consecutive, or they're going to be inserted into result one after the other. And then all I have to do to make the example work is to add one more element to each of these sequences, say an 8 in this one and a 9 in that one. So I want you to pause the video and to think about how I built these sequences and what's going to happen when you run the merge algorithm on them. So hopefully you realize that what must happen is that the first m minus 1 elements of the first sequence are going to be added to result first. So all of these elements get taken out. Now there's one element left in the first sequence, so the algorithm doesn't end yet. And because all of these elements are smaller than 8, the next phase of the algorithm will be to process these n minus 1 elements in the second sequence. So these ones get added to result. And notice what happens is we have one element left in the first sequence, one in the second sequence. So there's one more step that must be executed, namely to process this element. And now the first sequence is empty, the algorithm terminates, or rather the while loop terminates. But the question is, how many iterations of the while loop were executed in this case? Well, there must have been m iterations just to process the first sequence, and then n minus 1 to process the second sequence, up to but not including the last element in that sequence. So the total number of iterations were m plus n minus 1. And I'll let you think about whether it's possible for every value of m and n, here m was 5 and n was 4. But you should realize that for any value of m plus n, you can always build a pair of sequences like this one, where the total number of iterations of the while loop is m plus n minus 1. And therefore, the worst case time complexity of this algorithm for any value of m and n is on the order of m plus n minus 1, which is clearly not only big O of m plus n, but it's also big omega of m plus n. Since the minus 1 doesn't matter in the big omega analysis like it doesn't in the big O, the runtime is not only upper bounded by m plus n, but it's also lower bounded by m plus n. So in conclusion, we can wrap up this worst case time complexity analysis by stating that the runtime of this algorithm is big theta of m plus n. So m plus n is the total length of the two input sequences, and what we just concluded is that this algorithm is a linear time algorithm. If you take m plus n as a single value, then the runtime of the algorithm is just directly proportional to that length. So this is a pretty fast algorithm. It's a linear time algorithm, and we're going to use it in the next segment as a helper function for the merge sort algorithm.